MV302 and MV303 are solenoid valves. In our case, they are closed. This is our input-output diagram. Our input is motor power in terms of percent, and our output is water flow rate in terms of pounds per minute. This is a sample of our system at 60% input. The average flow rate was found in the steady state region, and for this particular region it was 12.1 pounds per minute with a standard deviation of 0.8 pounds per minute. We did this for a number of pump performances, and our output range was from 7 pounds per minute to 20 pounds per minute. Our gain was 0.28 pounds per minute per percent. Next, I'm going to talk about the step response of our system. The step response is a step in the motor power at a particular time, and the output is in pounds per minute. This is a sample step response from 45 to 60%. The step occurred at 45 seconds. The dead time was 0.5 seconds. The time constant was found using the Fit2 method, and this method involves taking the range of the output, which was 5.1 pounds per minute, and the time constant was found to be 1.2 seconds. The way the gain was found, the gain is delta C over delta M. The change in the output, which was 12.3 minus 7.2, was divided by the change of the input, which was 60% minus 45%. The resulting gain for this particular system was 0.34 pounds per minute per percent. These are our overall gain results. Our overall gain average was 0.29 pounds per minute per percent. These are our overall dead time results. Our average dead time was 0.52 seconds. Our overall time constant was 1 second. Next, I'm going to talk about FOPDT modeling. The FOPDT modeling is mathematical modeling of our step responses. It uses this equation down here, and for this particular model, from 60 to 75%, our gain was 0.3 pounds per minute per percent. Our dead time was 0.6 seconds, and our tau was 0.7 seconds. This is a chart comparing our step response and our modeling data. The average, you can see, is very, very close. It's very close to 0.3 pounds per minute per percent, which agrees with our steady state operating curve gain. This is the dead time comparison. The average of the dead time is 0.6 seconds. You can see from the upper range, the dead time is very close. The middle range, it's close to 0.5 seconds, and in the lower range, it's close to 0.55 seconds, which, relatively speaking, that's very close. This is our data for the time constant. The average for the time constant is about 0.8 seconds. I don't know why it's cutting off the seconds. I'm going to use this one. It's more reliable data over here. This is next I'm going to talk about our frequency response. The frequency response is varying the input sinusoidally, and our output is going to be in pounds per minute. This is a sample sine response with a frequency of 0.2 cycles per second. The amplitude ratio was found by using delta C and delta M, and delta C was found by taking the mid-range of the lower, the mid-range of the higher minus the mid-range of the lower, The delta M was found by finding the range of the input value. And again, the amplitude ratio was delta C divided by delta M. The phase angle is found by taking the little t divided by bigger T, multiplying that by 360. Little t was found by taking the shift from the input peak and the output peak. And delta t is the difference between the peaks down here. These are our Bode plots for our lower range. The gain was 0.6 pounds per minute per percent. The ultimate frequency was 0.6 cycles per second. Our KCU was 3.8% per pound per minute. And the ultimate frequency was found when the phase angle is at 180 degrees. It's 0.6 cycles per second. This is our Bode plot of our middle range. The ultimate frequency was 0.7 cycles per second. Our gain was 0.5 pounds per minute per percent, and our KCU was 3.7% per pound per minute. Our Bode plot of our higher range data, the ultimate frequency was 0.5 cycles per second. Our gain was 0.7 pounds per minute per percent, and our KCU was 2.6% per pound per minute. This is a close-up view of the frequency to amplitude graph. It says the same thing that the previous graphs did. The dead time was found using this equation. W is found by taking the equation W is equal to 2pf, P is equal to pi, and F is equal to the frequency at which 180 occurs, which is, for this graph, is 0.6. The equation was rewritten to find dead time, and for this graph, it's 0.99 seconds. This is our mid-range Bode plot data. The dead time for this data was 0.6 seconds. This is our Bode plot for our lower range data. And the dead time for it was 0.8 seconds. This is our modeling for our mid-range data. The gain was found to be 0.5 pounds per minute per percent, and the tau was found to be 0.8 seconds. We had a little bit of variability in our data. That is probably due to the noise of our system. This is a modeling of our upper range data. The gain was 0.7 pounds per minute per percent, and the tau was 0.5 seconds. These are our results of all four of our tests that we did. There is a little bit of variability, but overall, for the gain is about 0.4, 0.5 pounds per minute per percent. The dead time was 0.7 seconds on average. The tau was about 0.8 seconds. The ultimate frequency, the highest that we got was 0.7 cycles per second. That's for the middle range data. Our highest KCU was also in our middle range data, which was a 7% per pound per minute. If I were using this station, I would stick to the middle range of our data. So in conclusion, our tau average was 1 second. Our dead time average was 0.8 seconds. Our average gain was 0.6 pounds per minute per percent, and our frequency ultimate average was 0.6 cycles per second. Our KCU average was 5.4 pounds per minute per percent.